Bismillahirrahmanirrahim. Today is our lecture number 19. Our topic is exact sequence. So today we have studied about exact sequence. First of all, we have studied what is sequence. After this, we have started exact sequence. So we have also revised in the Dr. Dekasab notes what is exact sequence, type of exact sequence. So there are some related theorems we have already studied. But here I have also revised it. Number first, what is sequence? So sequence basically is a function whose domain is the set of natural number. Uh, whose domain is the set of natural number. After this, we have started what is the definition of exact sequence. So before this, we have started some definition. So let's start from definition. Yesterday we were studying some theorems. I think you should revise it. So let a sequence of R module and their homomorphic like this. Mn is a module, this is also module, this is also module. It is a sequence which is Mn minus 1 is a module, Fn is a function between Mn minus 1 and Mn, and Fn plus 1 is a function between Mn and Mn plus 1. Is said to be exact at Mn if and only if image of Fn is equal to kernel of Fn plus 1. This is the definition of exact. After this, we have revised some remark. The above sequence is said to be exact if it is exact at each Mn. Exact means that image of Fn means that you have revised image of Fn. So the image of Fn is in here, coming from Fn, and the kernel of Fn plus 1. So basically, kernel contains those elements of a function Fn plus 1 which we are taken from here, assigned to a function. This result will be identity in here. So kernel of F basically contain here the elements contain of this set. So this must be equal for exact. After this, we have revised another definition. An exact sequence of the form like O to O approach Mn, M dash, M dash, we define a function from M dash to M, and G define again a function from M to M double dash, and M double dash approaches to O again. Is called short exact sequence. What is short exact sequence? Short exact sequence is contain basically 4 modules like O, M dash, M dash, and double dash. So O approach O, the head of the arrow goes to M dash, and M dash arrow of the head of the arrow is move to M, and we are defined two function F and G. F is between M dash and M, and G is between M and M double dash. So in this type sequence is called short exact sequence. After this, we have discussed some remarks. Any exact sequence can be split into short exact sequence. After this, we define some definition. F is a function from M to N is an R homomorphic. Basically, F is a function which is defined from M to N, M and N are R module. He said that it is R homomorphism, so it should be satisfy the following two conditions. Number first, f of m1 plus m2 is equal to f of m1 plus f of m2. Number second is f of rm1 is equal to rf of m1. Then m divided by kernel of f is called co-image of f and is denoted by co-image of f. N divided by image of f is called co-kernel of f, and it is denoted by co-kernel of f. So this is some definitions related to our results short exact sequence and split and exact sequence we have already revised in the chapter like sub notes. So if you have want to again study, so you must see this lecture. So after this we have start the statement of the theorem. For R module A, B and R homomorphism, A and B are R module which is homomorphic if from A to B. This is also satisfy the homomorphic condition. After this we have proved that O approach to A. For this is not approach, this is basically we have defined function from O to A, but I have used here approach. So O approach to A and A approach to B under function f is exact if and only if is monomorphism. Number second, A approaches to B based on function f, and B is approaches to O is exact if is apomorphism, and O approaches to A approaches to B based on function f, and B approaches to O is exact if and only if is isomorphic. So I have revised the definition of monomorphism, apomorphism, and isomorphism. So for monomorphism, we have proved there two conditions. Number first, basically, we have proved there two conditions. Number first, isomorphism. Number second is 1 1. For apomorphism, we have proved that isomorphism plus 1 2. And for homomorphism, isomorphism, we have proved that homomorphic plus bijective. So this theorem is straightforward. The proof of this theorem, I think, available in the notes of Dr. Lekasa. Otherwise, you are do it self. After this, we have discussed some remarks. Let A be in R module, B be in submodule of A. Basically, A is R module and B is the submodule of A. Then alpha from B to A be inclusion map, and B from A divided by B be a natural projection. That is, B, we are taking element A from A. We are assign A to function beta. The resultant value will be A plus B, which must belong to A divided by B. Then alpha is monomorphism, beta is apomorphism, and image of alpha equal to B equal to kernel of beta. Thus the sequence like this is an exact sequence. So if you have feel any complication in this theorem, this is very easy, simple, straightforward. So you should contact with me. After this we have study in a next page. So after this we have studied some examples. If a function f from A to B is monomorphism of abelian group. What is abelian? Abelian, basically G is a group which satisfy, group means they satisfy the four conditions. For abelian group it satisfy the five conditions. So GBNM is said to be abelian if satisfy the following five condition. Number first, closed associative identity inverse and commutative law. If the binary operation is multiplication, so you should use multiplication. If the binary operation is addition, so you should use addition. So example state that if from A to B is homomorphism of abelian group, then the following sequence like O to kernel of F to A, and A to A by kernel, and A by kernel to O. And similarly the sequence O to image of F to B, B to B by image of F, and B to image of F to O are exact sequences. After this we have revised another example. I think we have also already studied in ring theory. Let R be a ring with unity, and if what is the ring? Basically R is non-empty set with two binary operation, addition and multiplication. For example, we are taking a particular operations, addition and multiplication. So addition will be abelian group R, and the multiplication will be semi group and left and right distributor R. Then we say that R is a ring. Unity mean that identity. Unit mean inverse. So F from M2 to Rm2 is basically contain a matrices of order 2 cross 2, and it's mapped to R4. R4 means that it's contain 4 dimension like V1, V2, V3 like ABCD. Also be defined by, we are taking 2 cross 2 matrix from here assigned to a function f. The result will be vectors which contain whose dimension are 4. Then f is isomorphism, and the sequence O to M2, M2 to R4, and R4 to 0 is an exact sequence. After this, we have all this theorem already we have studied in Dr. Lekasab notes. F A approach to B and B approach to C, and the function defined between this, between A to B, define a function f, and G is defined between B to C is exact, then G composition f will be 0. So we already studied this theorem. You should revise it. If you feel any complication in this theorem, you will contact with me. After this, we will go to next page. And this theorem is also very important. This is based on basically sequences, and basic also composition of functions are also used in this theorem. So let's start the statement of the theorem. For this, we have let A, B, C be in R module, and f from A to B. F is a function which defines from A to B, and G be a function which defines from A to C. Be R homomorphism. These functions are also R homomorphism. Then the following conditions are equivalent. There exists a mapping H from B to C such that H composition f is equal to G. Number second, for all x, y belong to A, f of x is equal to f of y, then g of x is equal to g of y. So by taking help from here, so we have proved that the following things. So we have started the proof from 1 to 2. So we have supposed that there exists a mapping H from B to C such that H composition f is equal to G, then prove that f of x is equal to f of y, then prove that g of x is equal to g of y. So from 1 to 2, we suppose that f of x is equal to f of y, then prove that g of x is equal to g of y. So for g of x, we have start from left side. So g of x, for instead of g, we put that from here H composition f. So we put that H composition f. Then we open the composition of these functions. So h f of x is also by hypothesis equal to f of y. So we put is equal to f of y. Then we again use the composition laws. So h composition f of y, and by again using this property g of y. So we assume that f of x is equal to f of y, then prove that g of x is equal to g of y. So the proof of this result is very easy. And similarly, you should prove that for all x, y belong to A, f of x is equal to f of y, then prove that g of x is equal to g of y. So this is very simple, straightforward. You should try. If you have feel any complication in this theorem, you must contact with me. Inshallah, we will meet in next lecture. Hafiz.